wiring a dock, especially one fed by a 480/240 transformer located away from the shore, it's crucial to understand the grounding requirements for separately derived systems. The National Electrical Code, or NEC, mandates specific grounding procedures to ensure safety and protection from electrical hazards. Firstly, bonding the transformer case to the neutral on the secondary side is essential. This establishes a common reference point for the electrical system. Secondly, running a ground wire from the transformer case back to the shore is also required. This ground wire serves as a low impedance path for fault currents, helping to quickly trip circuit breakers and prevent electrical shock. Thirdly, installing a ground rod near the shore is another important step. This ground rod provides a direct connection to earth, further enhancing the grounding system's effectiveness. The NEC specifies that the ground rod must be driven into the earth to a depth of at least 8 feet to ensure good contact with the soil. The ground wire must be sized according to the NEC guidelines. These guidelines take into account the size of the conductors supplying the transformer and the potential fault current levels. Using an undersized ground wire can be dangerous, as it may not be able to safely carry fault currents, leading to overheating and potential fire hazards. Additionally, depending on the dock's location and exposure to lightning strikes, you may need to consider installing additional lightning protection measures. These measures can include lightning rods, which are designed to intercept lightning strikes and safely conduct the current to ground, and surge protection devices, which protect sensitive electronic equipment from voltage spikes caused by lightning or other electrical disturbances. Here is a breakdown of the key steps to follow when grounding a separately derived system on a dock. 1. Bond the case of the transformer to the neutral on the secondary side. 2. Run a ground wire from the transformer case to a ground rod installed near the shore. 3. Drive the ground rod into the earth to a depth of at least 8 feet. 4. Install additional lightning protection measures if necessary. By adhering to these steps and consulting the NEC, you can ensure that the dock is properly grounded and protected from electrical hazards. Proper grounding is not just a code requirement, it is a critical safety measure that protects people and equipment from the dangers of electrical shock and fire. Grounding ensures that metallic parts of the electrical system are at or near ground potential, minimizing the risk of electric shock if someone comes into contact with them. It also provides a low impedance path for fault currents, allowing circuit breakers to quickly trip and energize the circuit in the event of a fault. This helps to prevent equipment damage and reduce the risk of fire. In addition to grounding, bonding is another important concept in electrical safety. Bonding involves connecting together all metallic parts of the electrical system, such as conduit, enclosures, and equipment frames. This creates a continuous electrical path that helps to equalize voltage potentials and minimize the risk of electric shock. Bonding is typically accomplished using bonding jumpers, which are short lengths of wire that connect the various metallic parts together. The size of the bonding jumpers must also be selected according to the NEC guidelines. The NEC provides detailed requirements for grounding and bonding in Article 250. This article covers everything from the size and type of grounding conductors to the location and installation of ground rods. It is essential to consult Article 250 when designing and installing electrical systems to ensure that they are properly grounded and bonded. The NEC also addresses the grounding of separately derived systems in Section 250.30. This section provides specific requirements for grounding transformers, generators, and other sources of electrical power that are not directly connected to the utility grid. The requirements for grounding separately derived systems are generally more stringent than those for grounding systems that are directly connected to the utility grid. This is because separately derived systems are more likely to be isolated from ground, which can increase the risk of electrical shock. One of the key requirements for grounding separately derived systems is the installation of a grounding electrode system. This system must consist of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The grounding electrodes must be installed in accordance with the NEC guidelines, and they must be connected to the separately derived system using a grounding electrode conductor. The size of the grounding electrode conductor must also be selected according to the NEC guidelines. In addition to the grounding electrode system, separately derived systems must also be bonded to the building's grounding system. This bonding is typically accomplished using a bonding jumper that connects the separately derived system's grounding electrode conductor to the building's grounding electrode system. The size of the bonding jumper must also be selected according to the NEC guidelines. The NEC also addresses the grounding of specific types of equipment, such as motors, transformers, and generators. These requirements vary depending on the type of equipment and its location. It is essential to consult the NEC for specific grounding requirements for each type of equipment. Proper grounding and bonding are essential for electrical safety. By following the NEC guidelines and consulting with a qualified electrician, you can ensure that electrical systems are properly grounded and bonded, protecting people and equipment from the dangers of electrical shock and fire. In the context of the dock wiring scenario, the 480/240 transformer creates a separately derived system. This means that the secondary side of the transformer is electrically isolated from the primary side and the utility grid. As a result, it is necessary to establish a new grounding system for the secondary side of the transformer. This is typically done by bonding the transformer case to the neutral conductor on the secondary side and installing a grounding electrode system, as described earlier. The grounding electrode system should consist of a ground rod driven into the earth near the shore. The ground rod should be connected to the transformer case using a grounding electrode conductor. The size of the grounding electrode conductor should be selected according to the NEC guidelines. In addition to the grounding electrode system, the separately derived system should also be bonded to the dock's metal structure. This bonding helps to equalize voltage potentials and minimize the risk of electric shock. The bonding should be accomplished using bonding jumpers that connect the transformer case and other metal parts of the electrical system to the dock's metal structure. The size of the bonding jumpers should also be selected according to the NEC guidelines. The NEC also addresses the grounding of electrical equipment on docks in Article 555. This article provides specific requirements for grounding receptacles, lighting fixtures, and other electrical equipment that are installed on docks. The requirements for grounding equipment on docks are generally more stringent than those for grounding equipment in other locations. This is because docks are often exposed to water, which can increase the risk of electrical shock. One of the key requirements for grounding equipment on docks is the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small ground faults and quickly interrupt the circuit, preventing electrical shock. GFCIs are required for all receptacles that are located within a certain distance of the water. The NEC also requires that all metal parts of the electrical system on docks be bonded together. This bonding helps to equalize voltage potentials and minimize the risk of electric shock. The bonding should be accomplished using bonding jumpers that connect the various metal parts together. The size of the bonding jumpers should also be selected according to the NEC guidelines. In addition to grounding and bonding, the NEC also addresses the use of overcurrent protection devices on docks. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. The NEC requires that all electrical circuits on docks be protected by overcurrent protection devices. The size of the overcurrent protection devices should be selected according to the NEC guidelines. The NEC also addresses the use of wiring methods on docks. The wiring methods used on docks must be suitable for the wet and corrosive environment. The NEC recommends the use of corrosion-resistant wiring methods such as liquid-tight flexible metal conduit, or LFMC, or a rigid polyvinyl chloride conduit, or PVC. The NEC also addresses the use of lighting on docks. The lighting on docks must be adequate to provide safe illumination for people using the dock at night. The NEC recommends the use of weatherproof lighting fixtures that are designed to withstand a harsh marine environment. Proper grounding, bonding, overcurrent protection, wiring methods, and lighting are all essential for electrical safety on docks. By following the NEC guidelines and consulting with a qualified electrician, you can ensure that electrical systems on docks are safe and reliable. The specific size of the ground wire needed depends on the size of the conductors feeding the 480/240 transformer. You will need to consult NEC Table 250.122 to determine the minimum size of the equipment grounding conductor based on the size of the ungrounded conductors. For example, if the ungrounded conductors are 1/0 American wire gauge or copper, then the minimum size of the equipment grounding conductor would be 8 AWG copper. Remember to always consult the latest edition of the NEC and local electrical codes for the most up-to-date requirements. It is also highly recommended to consult with a qualified electrician to ensure that the dock wiring is done safely and in compliance with all applicable codes. Neglecting proper grounding and bonding can have serious consequences, including electrical shock, fire, and equipment damage. It is always better to err on the side of caution and ensure that the electrical system is installed correctly and safely. Furthermore, consider the environmental factors at play. Being near the water increases the risk of corrosion. Using corrosion-resistant materials and proper installation techniques can extend the life of the electrical system and prevent future problems. Regular inspections and maintenance are also important to identify and address any potential issues before they become major problems. Look for signs of corrosion, damaged wiring, and loose connections. Addressing these issues promptly can prevent costly repairs and ensure the continued safe operation of the electrical system. In summary, grounding a separately derived system on a dock requires careful attention to detail and adherence to the NEC. By following the steps outlined earlier and consulting with a qualified electrician, you can ensure that the dock is properly grounded and protected from electrical hazards.